The next quantity we need to define in order to describe motion is velocity. We've talked a little bit about velocity so far. Velocity is a vector. It tells you how fast you're going and what direction you're going in. So there's a distinction between velocity and speed. Speed is just how fast you're going without regard for direction. But velocity, being a vector, includes direction. The mathematical definitions of speed and velocity look like this. Speed is the length of the path that you take to go from starting point to ending point, divided by the time it takes. You might have seen the formula d over t, distance over time, before for speed. Velocity is the displacement that we just learned about in the previous video divided by the time, or delta x divided by t. We usually use delta t to indicate the amount of time something takes. Just kind of traditionally use t here and delta t here, even though they really mean the same thing. So let's understand the difference between these two by doing a few examples. So in my first example, I'm going to use the situation from the previous video, the displacement video, where we had a car that started out at 10 meters, drove to the right to 30 meters, and then backed up to negative 20 meters. So let's calculate the average speed and average velocity as the car moves from location B to location C. I'll remind you of all this as I'm doing it. Again, using the numbers from the previous example, the time at this position was 10 seconds. So this position would be x initial. And then it moves to location C, which was negative 20 meters. So we'll say at position to C, you have a final x position of negative 20 and a final time of 25 seconds. So let's calculate the average speed and average velocity of this car as it goes on this short trip. So the average speed is distance divided by time. Now the distance to go from positive 30 meters to negative 20 meters is 50 meters. Remember, with speed, it's a scalar, so we don't care about direction. We only care about that distance, that path length between locations B and C. This guy was making noise. Don't scratch the chair. All right, so that was a distance of 50 meters. And the time it took was 15 seconds, going from 10 to 25 seconds. Now the average velocity is the displacement divided by time. And that, this is 3.3. With units of meters divided by seconds. Now the average velocity is displacement divided by time, so x final minus x initial over t final minus t initial. X final was negative 20 meters, x initial was 30 meters over 15 seconds again. So that is negative 3.3 meters per second. So for the speed, we didn't care about the direction. We only care about the magnitude. So we didn't include a negative sign. And in some sense, we're not really including a positive sign either. This number isn't really negative or positive, it's just a magnitude. For velocity, there is a minus sign. It's telling you that the car was driving to the left with a speed of 3.3 meters per second. So the velocity is 3.3 meters per second in the left direction. All right, let's do another example. Let's say that you run, but you'd have to be pretty fast to do this, but let's imagine you could do it. From a position of 0 meters to 25 meters, back to 0 meters in 5 seconds. So you start out, let's say 0, you run to 25, you turn around and go back to 0. Let's calculate your average speed and your average velocity. The average speed is distance over time. The distance you cover is 50 meters because you go 25 meters and 25 meters back. So that would give an average speed of 10 meters per second, which means you're a world-class runner. The average velocity delta x over delta t, x final minus x initial over 5 seconds, or delta t. For this situation, your final position and your initial position are both 0. So this ends up being 0 minus 0 over 5 seconds, which gives you an average velocity of 0. So this might seem kind of strange, but remember, velocity is telling you the displacement divided by time. Your overall displacement is 0. You went over here, you came back, and when all is said and done, you haven't gone anywhere. You haven't ended up at a different place than you started. So this is really the difference between path length and displacement. Displacement's only your change in position from start to finish. If you end up in the same spot you started at, that's 0 displacement, and that would lead to zero average velocity for that motion. All right, let's talk about a few more things related to velocity. Let's look at a graphical interpretation of what velocity means. So you might have seen in math class that velocity is the slope of the position versus time graph. If you haven't seen that before, you're seeing it now. So here's a possible position versus time graph. Here's position measured in meters. Here's time measured in seconds. You could have a graph that looks like this. This would be a graph of constant velocity. What I mean by that is that the slope of this graph, the slope, remember, is the change in x divided by change in time, or change in this coordinate divided by a change in that coordinate. This is the same everywhere on the graph. It's always going to give you the same number. So this slope, which is change in x over change in time, the velocity, is a constant number. It's the same value no matter where you do that little calculation along this graph. On the other hand, you could have a position versus time graph where the velocity is not constant. That would happen if your position graph has some wiggle to it. Maybe like this. In this case, your slope depends on where in the graph you're looking at. So for this section of the graph, your velocity would look like this. For this section, it would be a negative value. It's changing everywhere. So this is a non-constant velocity, a time-varying velocity. All right, one more topic. This is instantaneous velocity. Now, we don't do calculus in this class. Hey, the cat's running around. We don't do calculus in this class, but this is one concept that's kind of calculus related, but you can understand it without having to do calculus. The idea of instantaneous velocity is that it's your velocity at a particular point in time. You're not calculating a difference in displacements and And delta t's, you're not doing this. You're not doing a rise over run calculation. You're asking, what's your velocity right now? So this is the speed and direction at a particular instant in time. Mathematically, you would define instantaneous velocity as a limit of the average velocity when that time interval gets really, really small. That's something you do in calculus class. That's the technical definition. But we can understand this conceptually. Just think about going on a road trip. Say you're driving from LA to San Francisco. Now maybe the whole trip takes you 6 hours and it's like 360 miles to get there. Your average velocity would be 360 miles per hour going roughly north. But of course you're not driving at a constant velocity of 60 miles per hour north for the entire road trip. You have to pull out of your home and drive on surface streets for a while. You might have to make a few turns. So for part of your trip, you may be going 15 miles per hour east. For part of your trip, you might be going 0 miles per hour when you're at a stop sign or a red light. And then you manage to get on the 5 freeway and now your velocity is 75 miles per hour going north. And it all averages out to 60 miles per hour north for the whole trip. But at any particular instant in time, your velocity may be vastly different than the average velocity for the whole trip. So instantaneous velocity is your velocity at a particular moment, and it may or may not be the same as your average velocity. Now going back to these two graphs, the instantaneous velocity is the slope right at a particular point on your graph. Slope of that line right there. And notice that for a straight line position versus time graph, the instantaneous velocity and the average velocity are the same, because the slope is the same everywhere, so it doesn't matter whether you average over a big time or a tiny time, you get the same number either way. So for this graph, instantaneous velocity equals average velocity, but that's not true in general.